Okay, many objects oscillate, but we're going to look at a special type of oscillating motion called simple harmonic motion. The object needs to satisfy two conditions in order to do this simple harmonic motion. The first one is there needs to be a force on the object which is directly proportional to the displacement of the object from the equilibrium. In other words, the bigger the displacement of the object from the equilibrium, the bigger the force on the object. And secondly, the force is in the opposite direction to the displacement. In other words, it's a restoring force, meaning that the force is going to pull the object back towards the equilibrium position. Okay, here's an example. So we've got a mass on a spring like this. If it's at the equilibrium, there's going to be no resultant force on it, so it just remains there. Let's say we displace it, we pull it towards the right by 2 centimeters. So displacement is plus 2 centimeters. There's going to be a force on it, and it's going to be in the opposite direction to the displacement. So it's actually going to be a negative displacement. Like this, for example, we've got minus 10 newtons here. So the fact that these are two opposite directions, so the displacement is positive, the force is negative, is the second condition that the force is in the opposite direction to the displacement. In other words, it's trying to pull it back towards the equilibrium. Now I've pulled to the right by another 2 centimeters. So what I've done is I've doubled the displacement. This is going to cause the force to double as well. So it's gone from 10 newtons before when it was at 2 centimeters to 20 newtons. So this is the first condition, which was the force on that object is directly proportional to the displacement of the object from the equilibrium. This is not just true for force, it's also true for acceleration as well, because force is directly proportional to acceleration. So for example, let's say the acceleration at 2 centimeters or 0.5 meters per second, if I double the displacement, then my acceleration will also double, and it's going to pull it back towards the equilibrium. So what this means is that if I increase the displacement by some factor, then the force and acceleration will increase by that same factor as well, pulling it back towards the equilibrium with a bigger force or acceleration. Okay, these two conditions define simple harmonic motion. It can be written as an equation like this. Force is directly proportional to the displacement there, represented by x, but there's a negative symbol there to show the second condition, which is that it's in the opposite direction to the displacement. For example, if x is positive, the negative in front of the x will turn the force into negative. Okay, so, but if x is negative, then negative times negative gives us a positive force. You can turn this into an equation by just putting an equal sign and putting a constant, in this case k, which is convenient, especially for the example before, because the k is actually the spring constant in the previous example. But if it's a different scenario, a different type of object system doing some motion, the k can be anything. It will vary from system to system. And secondly, because force is direct proportional to acceleration, I can just say acceleration is direct proportional to displacement and the opposite direction as well. Okay, this can also be represented as a graph. So I've got force or acceleration on the y-axis and I've got displacement on the x-axis. I get a straight line because it's direct proportional, but it's also got a negative gradient to show that it's in the opposite direction, the displacement. Here's another example. So this is a pendulum here. So in this case, if it's at the equilibrium, there's no resultant force, so it just stays at equilibrium. But let's say I displace it in the positive direction, then it's going to have a negative force pulling it back towards the equilibrium there. So the displacement was towards the right, the force is here towards the left. Okay, so let's say I've displaced the pendulum even more towards the right, giving a bigger positive displacement. That would increase the restoring force as well because it should be directly proportional, pulling it back towards the equilibrium with a bigger force. And now I've displaced the pendulum towards the left, so that means it's a negative displacement because left is negative and right is positive. So if I give it a negative displacement, the force has to be in the opposite direction, so the force is towards the right. So it's actually a positive force now, pulling it back towards equilibrium. The diagram shows a buoy floating in water. It is pushed down into the water and released. The resultant force F on the buoy is given by the equation shown here. I explain how the equation shows the buoy will do simple harmonic motion. So in this equation, got F is a force, rho is the density of the liquid, A is the cross-section area, not the amplitude in this case, and G is the gravitational field strength, and X is the displacement of the object. So firstly, we're going to look for the condition for simple harmonic motion. Firstly, you can see force is directly proportional to displacement because these numbers here, rho, A, and G, are constant. So you can see it's just direct proportional. And secondly, you can see that it's got a negative at the front here, showing that if the displacement is positive, the force is going to be negative. The displacement is negative, the force is going to be positive. So it's a restoring force pulling it back. And these are two conditions you need for simple harmonic motion. So it will oscillate back and forth following simple harmonic motion. The diagram shows a torsion pendulum. It's basically a wire with a mass attached to the end of it, and that mass you can spin, you can turn it by some angle. And this is going to create some torsion within the wire, which is going to try to pull it back to its original position. So the mass at the end is turned by an angle theta. The graph shows how the torque, which means turning effect, on the wire and mass varies with angle. Okay. Describe and explain the motion of the pendulum when it is released. So firstly, we can be pretty confident it's going to do simple harmonic motion because you can tell from the graph it satisfies the condition for simple harmonic motion. How do we know? Well, firstly, it's a straight line. So we know the torque, which is basically the turning effect, restoring it back to its original position, is directly proportional to the angular displacement, how much you spin it from. The more you spin it, the bigger the torsion and the torque inside the wire trying to pull it back to its original position, and it's directly proportional. Okay, secondly, it's a negative gradient graph. Okay, so that shows that the torque is trying to return it to its original equilibrium position.